Hello everyone, welcome to another deep dive. If you're watching this after the fact, beware that you can check the note stock on the description on YouTube for time codes, so you can skip through stuff. We usually cover a lot in 2 hours worth of stream, so that's a great way to check out what we did. And I actually went back and did a read last week, so I would actually kind of have an idea of what I did last week. So today we got lots of exciting stuff. I'm not going to go into it quite yet. We're going to wait a little while longer to let people get going. And the cat is on my lap. He's funny. I had the door closed getting ready, and Spook was at, he doesn't meow all that often, but he meowed to get let in. So I thought that was cute. And yeah, he was just in a litter box. He got me. Anyway, so we're getting going. I won't do housekeeping quite yet because I still need to arrange my windows a bit better. And of course I have my desktop up. I was a little behind, just a smidge. Let's go to here. That explains. Let's say hi to folks before we do housekeeping. So I saw Musawi was waiting. Unexpected Maker. Good morning. Hello, Dave. Odessa. Mark Comus. Hello, Mark. I'm so used to Discord. Mr. Who 30 says so many streams, so few time. You gotta prioritize me. Bruce says I saw some video of CircuitPython on the Raspberry Pi. Spoilers. Hi, Piata. Hi, Pierre. You're just on time. I was a smidge late. Hi, Randall. Hi, Paul. Dave says haircut. Yep, definitely. Got a haircut yesterday. Hi, Minnesota Mentat. M. Lindholm says such a potentially useful stream. Nice been using CircuitPython and Adafruit models and sensors on Raspberry Pi lately to avoid memory issues. Unexpected Maker says your apartment has movable windows. I don't know what you mean by movable windows. I live in a house and this window is open right now because it was a little hot in here. Hello, Vignesh. Hopefully I said that right. Let's say hi to folks in the Discord. DCD's in the Discord. Thank you, David, for doing notes. Hi, Doctor. Hi, Patrick. Hi, Keith. Hi, Love the Factory. Mark's there again. Hi, Andrew R. Hi, Bruce S. And folks in Discord need a haircut. Yeah, I was lucky. I was able to schedule it pretty quickly. It was only a few days, so. Yeah, thanks for helping. I really appreciate it. Hi, Quarky. Welcome. Okay, so. Oh, let me pause my videos here. I don't need to see me delayed. I think YouTube will be a little bit more delayed than normal because I have it, arrange my windows before you get going. Yeah, the desktop windows. Let's see. I think I've got everything set up right. YouTube is on normal latency, so there may be a little bit more of a delay, but that's because the auto captioning only works in normal latency, and I think that's important. Twitch may be a bit quicker if you're concerned about how fast I see what you're saying. Let's do housekeeping. So, hello everyone, my name is Scott and I work on CircuitPython for Adafruit. Those are two things you may not have heard of, so let me cover them briefly. So CircuitPython is a version of Python designed for microcontrollers, typically, which are these little inexpensive computers that are really inexpensive. They have a lot less megahertz power, like CPU power and RAM, than is typical for something that runs a full operating system. CircuitPython itself is kind of like the operating system all in one. Yeah, so that's CircuitPython. Today I've been working on this weird world where we're putting CircuitPython on a Raspberry Pi, which is something that you can run a full OS on. So it's pretty exciting. And then I am paid by Adafruit to do these streams and the code that I work on. So Adafruit is an open source software and hardware company based out of New York City. I work remotely for them, so I'm actually in Seattle, and therefore I think of Pacific time zone stuff. Oh yeah, Spook's settling down. We had the cleaners earlier, so he didn't get to do his regular cat nap. Oh, he's coming back for more lap time, I think. Yeah, so that's Spook, the cat. He's been doing so well. I used to give disclaimers about his seizures, but he's just been doing so good. Let's see his face. Oh no! Cat cam down. I had it clipped in. He didn't run away though. Yeah, so Adafruit is based out of New York City. If you want to support me, you can support me indirectly by buying stuff from Adafruit by going to adafruit.com, checking stuff out there. I'm working on a firmware development and debugging gift guide. Lamore asked me to do this, so it's all the things. I basically just like stared at my desk and put the things that are on my desk in the gift guide. So keep an eye out for that. That'll come at some point. I don't know the timing. If you want to chat with me and a lot of others, you should join the Discord server, which is the middle box here. That is a place where we can chat all week long. We do CircuitPython development in that channel, so you can keep an eye on how things are going. And I gave a little bit of a spoiler about what I've been working on there last night because I got stuff going. That's Discord. So this is a deep dive. It happens almost every week, normally on Fridays at 2 p.m. Pacific, which is 7 minutes ago. We will shift. I was looking, it's like November 7th, so we have a couple more weeks until the US shifts time. So beware that in a few weeks it will it'll change a little bit. And it typically goes for 2 hours or more. We'll probably shoot for right around 2 hours like we normally do. We actually tend to have people fall off if we go over 2 hours. So 2 hours is a good amount of time that we all kind of like, I think, commit to. So that's the plan. If you have questions about what I'm working on, what I'm not working on, you're welcome to ask them. We know this is a very casual, chill stream. And so we're happy to get interrupted. But we've got lots to show, so we'll show that too. Oh yeah, Spook's in the main cam instead of the cat cam. I can adjust cat cam. So he's in both. Manual. So let's see. M. Lindholm says, oh, whoops, I'm using Blinka, not CircuitPython, prototyping on the Pi with Blinka before I move to an MCU with Circuit or Micropython. It'll be 2 Pacific Standard Time. So whatever time 2 p.m. here is. So I will not change what day or what time it is for me, but for folks outside the US, beware that we haven't done our time change yet. I think outside the US it has happened already. M. Lindholm brings up a point about using Blinka on the Raspberry Pi rather than CircuitPython, and this is a distinction that I've been trying to get us to make for years, because I knew I always wanted to do this native CircuitPython on Raspberry Pi stuff that we'll talk about more today. LinkedIn user says, "Woot, land of grunge." Indeed. Yeah. We've got a number of Seattleites in the chat here. Okay, so where we left off was actually, I looked back at the notes. Thank you again to David. And I was having trouble. We had gotten the REPL over the UART and been able to do 1+1, but we couldn't print hello world. And we were trying to figure out how to debug that. So I've made a ton of progress this week on this Raspberry Pi stuff. Not all just thanks to me, but we'll get into that a little bit later. Let me just kind of catch you up. So I figured out a way to do the backtrace stuff that we spent all last week doing. And so let me just start by showing that, because I think it's just kind of neat. And we should take a look at that. So let me actually just do it through GitHub. So on GitHub, there's this broadcom-peripherals repository that I've been working in. This is meant to provide like a CMSIS style layer for the Raspberry Pi, even though CMSIS is technically only for Cortex-M chips. There's some weirdness because Cortex-A chips can have virtual addresses. So like SVD files and that sort of stuff where like addresses are fixed doesn't quite work in a world where you can like remap addresses. But assuming that you're like not remapping stuff. So CMSIS is CMSIS. It's the CMSIS. What does it stand for? Common Microcontroller Software Interface Standard. So it's really common for microcontroller vendors who are all built around ARM to be using like standard ARM tooling to put their systems on chips together. So there's these core bits, and it's interesting that they do have some stuff for A5, 7, and 9. But this like the PAC and the SVD stuff are kind of like the things that I really like. So SVD files are system view description files, which tell you like what address ranges are all the different peripherals and what the registers do and stuff. Hi Timon Scoop, you're going to be very excited. Spoilers. Actually, I thought about digging out my Pioneer. Maybe I'll give that a shot too. Yeah, so where we left off was we were trying to get the backtrace working across an exception. And I'll show you how I finally figured it out. So there's this cortex-a gdb.py file. And this is where I've been putting kind of like, so GDB is the GNU debugger, and I can just show it too. So, I'm not showing my desktop. I'm sorry about that. So if I want to, so I can do openocd to connect to it, and then I can do tar ext. So let's like target external this port. And what you can do is if you have it in a source, you can do, or you can source peripherals Cortex. What file am I in? Cortex-a GDB. So what that does is it gives me this ARM v8a exception. Oh, I hope you're feeling better. It's not going anywhere. So nothing happened because we're not in an exception. But if we go back to the file, which I don't think you could see until now, and I'll dump the link in the Discord. So what you do is you take this file and you source it into GDB, and that gives you this ARM v8a exception. And then further down, what I finally figured out how to do was you can actually do unwinders in Python as well. So what that is a backtrace is a thing that shows you like where you are. So like starting from main and then what functions were called. So this is GDB here. And you can see that we're like in this enable interrupts thing right now. I think if I do, so you can do breakpoint, and I think timer one handler will, that won't work. I don't think that works. But basically we were having, when we were loading the wrong file and it wasn't working, we were having trouble like seeing kind of past the exception that was triggered by the error. And so what I finally figured out is that there's two critical bits to adding your own unwinder. So what you get is a pending frame, and it gives you where the stack pointer is for this frame and the program counter. And in order to kind of consider a full frame, what you have to do is you have to then say, there's this pending frame create unwind info, and you give it an ID. And then what you can do is you can add saved registers. And it's important, the thing that I was missing is that you need to add 4 this is for ARM, you have to give both program counter and stack pointer updates into those add saved registers. And in addition, you want to like put, so this is saying 4 registers in these read the memory off the stack to figure out what the values were, and then add the saved registers to that unwind info. So that's kind of restoring the state of the stack in terms of registers, and that's good for your backtrace for like values and stuff that were passed around. So this is meant to, the order of these registers that we're reading off the stack is meant to match the boot.S way that it like saves all the registers. So I figured that out. It works now, as far as I can tell. So it only works if it's in a hard. I added a hard fault handler. You can see here that it's in, if hard fault is not in the string or IRQ is not in the string, then it doesn't work. It won't like try to use this unwinder to figure out the frame. So I did that, and this was all trying to figure out why I couldn't print a string, and I was getting like that address that was wrong. And I finally realized that Micropython and therefore CircuitPython have different ways of representing objects. I don't know if I talked about this before, but there's a good explanation in mpconfig.h. So there's 4 object representations. There's A, B, C, and D, and they get kind of like more complex as you go further down. And this object representation C is actually what we use kind of in all the microcontrollers, and it has this nice property that it can store data in the pointer itself, which means that you don't have to always go to the heap to allocate some things. So here you can see, and it's probably dark and small. Let me make it a little bit bigger. Hopefully it's a bit easier to read. In Micropython and CircuitPython, this is mpconfig, where these comments are. But you can see here that they lay out all the bits of the pointer and basically say that like pointers on this architecture have to be 4-byte aligned. So if the last 2 bits are 0, then we know that it's a pointer. Otherwise, we can actually put like values in that those 2 bits to indicate what it actually is. It's kind of fancy. Anyway, so I was using this. I had set it up to do object representation D because it's for 64 bits. But what I didn't realize is when I looked back at like the history of this, it was added for doing 64 bits, but on a 32-bit system. So there was some weird stuff that it was doing to like account for the fact that it was pretending to do 64 bits, but in a 32-bit system. And I guess we can see that here too. So for the pointer, like the pointer is still only 32 bits. So I was trying to use a 64-bit representation designed for 32-bit CPUs on a 64-bit CPU, which was a problem. So I looked and I figured out, so Micropython does run in 64-bit mode because it can run on Linux and Unix and stuff. And it turns out it's just set up to do this object representation A, which can work for any number of bits. So we'll have to use the heap more for some data, but besides that, we can just use object representation A. So I switched to that, and suddenly I can print hello world. So that was really good. That was really good progress. And then the next thing I was working on is like, you know, we had UART, and I was like thinking I could circle back to USB. But I was like, you know, I think the thing that excites me most about bringing it to, that had to be a great feeling seeing the hello world print. Yeah, it was nice. It was like kind of silly because I had been like trying to fix up some of the object representation D stuff that I found. And it was just like, oh, I just shouldn't be using that, which is silly. So that was cool. And then the next thing I wanted to work on was the HDMI output, because that is something I think that something unique that the Raspberry Pi brings to things is its ability to do native HDMI. And so it's pretty straightforward. There's like good tutorials on it here. It's like, here's part 5 frame buffer. And they talk to you about like, you have to do, so there's this mailbox thing that I think we talked about. Yeah, the heap size should be more than adequate. Yeah, so I have the heap size right now fixed at 32 megabytes out of the like gigabytes that I actually have, which kind of boggles my mind. I don't know what to do with all of it. Although I think we might do some stuff with that today if we get there. So I did more mailbox calls, and there's this like very straightforward call to get a frame buffer from the GPU. So basically, it's not here. Basically, you do this frame buffer call that's like setting up how much physical frame buffer you want and how much virtual frame buffer. So that's like the virtual frame buffer size is the size you're actually going to output. The physical one is like how much memory you have. And there's a frame buffer, or there's a mailbox call that you can call to tell the GPU to move where the virtual one is. So that makes like scrolling and panning and stuff potentially like really quick and smooth. And I just like, in general, the Pi peripherals are really not so crazy to handle as I thought it might. I think like, you know, I think it's largely been kind of what I expected, where it was like, one of the big hurdles was just like moving to this Cortex-A land, where we have virtual, like the memory, the MMU, we have the different exception levels, and we have exceptions instead of interrupts. And so all of that, like, you know, I feel like we've gotten over that hump a lot, which has been great. Although there's just like thing after thing after thing. And I've like, when I've been like talking to more about it, and I know some of you saw that, it was just like, it's slow and steady progress. Like I get so far and then I hit this hurdle, and I get so far and I hit this hurdle. Yeah, so I like spent all of yesterday. I spent all of yesterday trying to get this frame buffer call working, and I have this, I got rid of it. When you do a frame buffer call, it will write a value and tell you whether it correctly was parsed or not. So it'll give you a status of like, yeah, it worked, or it didn't work. And if it didn't work, what I had it doing was just spinning so that I could find that it didn't work. And that's this. So if people want to know more about the Cortex-A stuff, this thing that I printed out, this PDF, the Programmer's Guide for ARM v8a, I highly recommend it. It's a great resource if you're just getting into doing these Cortex-A stuff. Like, I wish there was a video of this, and like a presentation to go over all this. I haven't been able to find a whole lot of stuff online about it. I have to clean my desk. Okay, so I spent like all Thursday trying to get it working, and I like went back to basics, and I was just like, I haven't seen any. So I haven't shown this. Let me give you a little bit more of a tour of my setup with CatCam here. Although I do have the overhead here too. So there's the kitty. He's like, are you talking about me? So my setup here that I have is I've got the CM4 IO board, and then I actually have this like 7-inch Elecro HDMI screen that I bought off Amazon. So I was using this to test HDMI, and I like went back to basics. I was not getting anything on it until the bootloader, like the Raspberry Pi bootloader, will actually show up on the display. So if let me just see if I can't show that. Let me see. So that's my setup. What I've actually got now also is it under the normal ARM pages? You know, I don't know where I found it. I think, oh yeah, well, there's the Programmer's Guide for ARM v7. Read guides for ARM v8. You want to see my desktop. A profile. Memory model. Oh man. Advanced features. So I have this open, the GIC. What is this? No. I'm sorry, I don't know where I got it. I would just Google it. Like, Google the name of it. It's like 2,000 pages long. Something like that. I'm sure it's somewhere here. Find the link to the PDF. Yeah, that looks right. And then if you download it, that's probably... Yeah, see, it's the second one I got. Yep, that looks right. Mototimo says, did you have EDID issues with the monitor? Between that and the refresh rates, embedded HDMI can be tricky. I am ignoring EDID right now. At least I'm not dealing with it. The GPU might be doing some stuff. I told Lady Ada I was working it on, and she was just like, you should do 640 by 480 to start, because that's what like all the devices she knows will support. So let me just see if this works. So I've actually got a cheap video capture thing plugged in here for the HDMI output from there. So what I'm gonna do is I'm gonna take out the SD card and see if this shows anything. I tried to test it. There we go. Nice. Okay, so this is the Beagle 5 has a low odd refresh rate and works with 0 of my monitors. Oh no. So this is what happens when I just took the SD card out of the Raspberry Pi. And this is what happens. Like, you'll get a display on the CM4 with that. So I'm glad that video is working. What I found yesterday after spending all day on it was that this test didn't actually work with this monitor that I've had here. And I was so frustrated. And then I looked more at the Raspberry Pi, or the CM4 IO board, and it was a little, like the module, it was a little tilted. And I looked more closely, and half the pins were not connected. So the CM4 has like 2 different pin connectors on it, and one side of it has like power and GPIO, and that one was set correctly, but the other one was like sitting on the connector, not. So I pushed it down, and it worked. I was like, how many weeks have I been using this setup and I didn't figure out that my CM4 module wasn't plugged all the way in? And I was like, oh, this is the worst. But again, it started working, and then the mailbox call then did work as well. And so I was like, okay, great. Like, I got it working. I just hadn't plugged it in right. And it hadn't been plugged in right for weeks. And then I was like, oh, you know what? This might have been my problem with the USB as well. I was like, let me look and see what pin USB is on, which of the connectors it is. And I pulled it up, and sure enough, USB is also on the other connector that wasn't plugged in right. So I took a glance at USB yesterday, and saw that like more was happening on the bus, but it still wasn't working perfectly. So that's as far as I got yesterday on USB. So let me just see. I think I actually have it turned off. So let me go and see if I can't get the display working. So I just commented out. Yeah, all the low speed stuff. So like Blinky, floating TX pin for Ethernet. I know, right? It's just, ugh. Okay, so let me recompile and load it again. And this is unhappy too. I'm in the wrong folder. Oh, and you can't see. Do I have? I do. Bad solder joint. Well, that's better than. Oops. Let's see. I might have to fix something. We'll see. That's okay. So I was actually trying to starting to do the SD card support. Hello, doctor. Will it build? Yay. All right, so let me figure this out. So copy it over. And do sync. And I wonder if I can just pop it in while it's unhappy. See what happens. Ah! Look at that. So it's currently set to do 640 by 480. It's just manually set. So we're not doing any detection of what the display is. But it does work. So if I go and this is over UART. If I type something in, it's pretty slow. But I can do print hello world. And that's nice and quick. It's the scroll that's really killer. So I can do 1 + 1. And then the scrolls are pretty slow. I actually had to fix a bug with this. So when I first got the output working, it was all jumbled up, and I should have taken a picture of it. It was all jumbled up, and it was all white. It was like white and blacks, and I could kind of make out like where the text was. So I had a pretty good idea that like I was close. Like I was writing to the memory, but I wasn't like. Yeah, the bad red diode. Yeah, totally. Just like ugh. Yeah. That scroll though. So one thing I wanted to talk about later is to see if we can't speed this all up. So right now, I should caveat, the reason that it's so slow, I think, is because right now we have no caches active. So every time it needs to load an instruction or load data, it is going all the way to memory to fetch it and back. So there's two levels. There's an L1 cache and an L2 cache that should speed us up a lot. It just makes things more complicated. So I think what we'll do probably in 25 minutes, I've got more updates, is I think maybe we'll try to turn the caches on and see how much quicker it is. That's actually also why I have it at 640 by 480, because I was able to output at 1080p, but it was even slower. So first thing is to get all the caches going, and then the second step is like we could potentially optimize how scrolls happen for the terminal IO class. Like, I was thinking about this, like we could have terminal IO like output one box to render per line, and then it could do computations of like if you're scrolling one and the tile, like the two tiles that you're scrolling are the same, then you know you don't have to update it, right? Anyway, so I've got ideas. I know the scroll's slow, but I think the caches is, I suspect that the caches themselves are going to be what speed us up. I did actually get blinking with digital I/O working. I showed it on Show and Tell on Wednesday, although I don't have all of the pins laid out yet. So if you do import board, dir board, you can see that I've only got like a couple pins defined right now. These are the 4 pins that I have LEDs on my breakout set for. Anyway, so I think there's a lot of yeah, the ESP32S2 and the RP2040s slow scroll as well. Yeah, so I think like there's definitely optimizations that we can do in terminal IO to optimize like the problem with terminal IO, right, is that it's a giant grid. It's a giant grid of values, and when you scroll it, it doesn't know like which parts actually changed. It just assumes the whole thing has changed. So you have to like recompute all the pixels for all of that whole area. So if you wanted to make scrolling faster, what you could do is you could take some time to figure out like which tiles change when you scroll and only update those. Yeah, and the more pixels you have, the worse that gets. But the Raspberry Pi should be pretty quick. So, and I know that like CPUs like this, is the unit of scroll size constant as you scroll? Yeah, so the way that this scroll works is, well, it's scrolling one. Well, I guess it could scroll more than one, but like when it does that, that's on a scroll of 1. Ooh, it says, I have a Pico and I'm trying to make a MIDI sequencer, but I can't get a precise ppqn clock using time.monotonic nanoseconds. I heard we can't use timer interrupts with CircuitPython. What should I do? I don't know what a ppqn clock is, but like time monotonic nanoseconds is pretty good. The problem is that like CircuitPython and Python in general is not like doesn't run consistently fast, because you're like managing memory, and some actions to manage memory take longer than others. DCD says, is there an API that does hardware GPU types support for scrolling? There is, and yeah, so that's the virtual frame buffer thing. You could use to do some scrolling. Yeah, that would help a lot, actually. Pulses per quarter node. Yeah. I don't have a good solution for you if you're trying to write UART out stuff on a precise timing. But the terminal I/O stuff is just not written for any hardware sort of support. Unfortunately, like I really wanted to support it. Like a lot of those, a lot of the SPI displays that we support in CircuitPython, they will allow you to shift, to wrap around the display for scrolling. The problem is that's only in one direction usually. And it's usually not the direction you care about, which is super unfortunate as well. So yeah, it's just like, it's probably worth instead of supporting hardware stuff, it's probably worth optimizing like a lot of what display IO does is figures out how, like, what areas of the screen changed. And so, like, we could have terminal IO optimize that more. And I think, like, Keith is alluding to, like, the faster you scroll, like, if you're shifting 5 lines at a time, like, the chance that you have the same things at the end, like, if each tile is the same at the end, is probably less likely. I don't know. You can figure that out, because the terminal or the tile grid stuff does know, like, I guess, yeah, tile grid will know how much it shifted between this refresh and the previous refresh. So yeah, there's definitely room to optimize that. It's always a trade-off with code size as well. So it's probably worth being behind a flag so that for small boards, we don't inherit that code, and they'll only support small displays, which is fine. Would this build work on any other version of the Pi or only the CM4? It should work on any Pi 4, I think. I think it should work on a regular Pi 4. The challenge is that the USB is on the power connector. Sparklebeard, oh, this is CircuitPython running bare on the Raspberry Pi 4. Correct. So what you're seeing now, this terminal output here, is HDMI 640 by 480 output from the Raspberry Pi running CircuitPython bare metal. Couldn't you define the display as larger than it is and mess with the start row to result in a scroll-like effect? Yeah. Right. Start row on the SPI LCDs, but almost always the start row is the wrong direction. Like, it's usually, like, the ribbon cable is showing you rows, and then more often than not, like, it's sideways. Like on a Pi Gamer, the ribbon cable's on the right-hand side, and the scroll the native scroll goes left to right, but if you're doing terminal, you're wanting to scroll vertically. It's really just not, you could optimize it, but there's going to be so many cases where you can't take advantage of the hardware scroll. All right, well, that's pretty cool, right? Well, let me... So I was like, oh, it was not working sideways, or it wasn't working because it wasn't seated all the way. And this bootloader test, where you take the SD card out and just make sure it shows up in HDMI, is a really good way to test that, that it is working. And I was like, okay, today I'll take a look at USB. However, well, I did look at USB today, but TAC pinged me last night and said, hey, I got it working. So I had asked him to take a look at it. Those of you who don't know, TAC is the creator and maintainer of TinyUSB, which CircuitPython is built on. Paid for by Adafruit, so Adafruit.com supports TinyUSB and TAC as well. He had taken a look at it. He got his I/O board, and he got USB working as well. So let me see if it works here. I'm gonna plug it in. So that doesn't mean that the drive is not working yet. It works on the USB side, but I haven't implemented the SD card side yet. So now if I go TO, maybe it'll work. I did have to fix a couple things. All right. So now we are connected over USB. I'm like, compared to where we were last week, I'm so excited. I was like so excited. Like, I was just about to go to bed and TAC was like, hey, I got it working. I was like, like, I had just gotten HDMI working and now we have USB working as well. He only got USB full speed working. But that's like normally what we have across all the microcontrollers. So it's totally good for what we're doing right now. Pierre says, could it be that it wasn't working for you because the board wasn't plugged in fully? So I did check. I did check that. I did check yesterday that the current code that I had put together did not work once I plugged it in. So I know that like TAC got it working. I did not. I didn't figure out the USB stuff. I had to fix the like CircuitPython side a little bit just to work with tiny USB. But yeah, I had to fix like there's a check in CircuitPython to know whether it's in an interrupt or not. Have a good walk, doctor. And yeah, so there's this check in the serial side to make sure that it doesn't output to USB, print statements to USB, blah, blah, blah. Anyway, it caused an exception, so I had to fix that. I feel like there was like one other thing. Actually, I could look and see what I've changed. Or did I commit it? Let's see what I've got changing here. Yeah, so this I haven't committed yet, and I will switch back to, oh, not that one. Switch back to here. So I switched to my tiny USB branch. I got the additional tiny USB stuff source to build. Yeah, teamwork for sure. Yeah, TAC is like awesome. Tiny USB is like growing. The tiny USB itself has like 2.1K stars. Like it's gonna surpass CircuitPython, which is totally cool. Because like it took me less than a day once tiny USB was working to integrate it into CircuitPython. It just makes like so having CircuitPython centered around tiny USB just like makes it so awesome. Hi, Anthony. Thank you. Awesome job. Yep. USB was TAC's doing. Thank you for the well wishes. Yeah, it's a ton of progress this week. It like finally came together, which is like super exciting. Oh, I guess one thing I should do for the display is make board.display work. So this is all display IO, so we should be able to just do any display IO stuff via it as well. But it is super slow, so I think it's worth poking the caches a bit. But in terms of getting USB working, I had to add the system core clock, which is not too bad. And then this is a check, like this is to see if we're in an interrupt, and I had to make sure that it didn't do. It was only for cortex-M. It was trying to read an address that wasn't mapped, so it was hitting the hard fault handler. Hard fault handler in air quotes that you can't see. Yeah, so that's working. I think maybe I'll just commit this. And if folks want to try it, I'd be happy to help you try it. It is slow. I will warn you, especially with the display on, it's quite slow. But that's kind of what I thought we could poke at for the next hour. But let me commit. Let's commit this first. So I think we want all of this. What does peripherals have changed? Oh, this just has the base address for the second eMMC. Let's just commit that now. Oh no, I reset hard. Oops. Yeah, so the next step I was trying to get going is that, so my plan is that the SD card will have two partitions. It will have two partitions. The first partition is the boot partition, and that will have the kernel 8, which is like CircuitPython. And then we'll have a second partition that will be the CircuitPy drive. And so what we'll do is we'll make that CircuitPy drive available over USB like we normally would. So what I did, I just like put my headphones on earlier and jammed out the registers for the eMMC peripheral, which is what you can use to read the SD card. Although there's a second peripheral called the SD host that you can also use, so I got to figure that out. What did I miss? So that's what I was doing earlier today, but that's not what I want to do for the next hour. I think that's the right memory address. I just want to get that committed. Okay. And then we'll switch to origin. Okay. And I think we just want all of this, but we can use merge to go through it. So yes, we want to use my copy of TinyUSB, the new version of it. We want this, and this, and this, and this. Oh yeah, I had to change endpoint pairs because I had a safe mode because I didn't have enough endpoints. Oh, and I had to call USB IRQ handler. I was calling TinyUSB directly, and that wasn't scheduling the follow-up stuff, which I realized. Okay. USB works. USB CDC works. It's possible that like HID and MIDI may work as well. Let me push that. Okay. Why did you need more endpoints? It was set to 0, and the new dynamic turn off and on USB stuff actually checks at runtime whether you have enough. Like if you set up your USB to use more than you have, then it will fail. Then it'll go into safe mode. So I guess it's fine because it won't change USB at that point. Okay, so I pushed that, and let's talk caches. And in fact, let's just pull up this. So this is what I have printed out. This Cortex-A series programmer's guide, and I read the chapter on caches last night. So I think it's always useful. It's always useful, or it's really important to reiterate how important caches are. This is something I learned in university, but then I think a lot of people don't fully appreciate it when they're looking at like different microcontrollers or different processors. Is that people will look at clock speed of the CPU, but they won't look at like cache sizes, cache hierarchy, and just like memory throughput. This is something that the Raspberry Pi team did really good job with the RP2040. Is that they have a really well thought out memory system, which means that although they're Cortex M0s, they can get a lot of data in and out. So, you know, here's main memory. This is like the RAM chip on your Raspberry Pi, but between there and like the CPUs, so the CPUs in this diagram, are they salted or unsalted caches? Unsalted. Did I say cashews? Cache issues. So what we have here is kind of like a diagram of a multi-core system. This is all ARM specific terminology. I don't really know the x86 version, so I can't really compare. But you'll see here that there's their core 0 and core 1, and they're in a cluster, and then could be a second cluster. In the Raspberry Pi chips, there's always just, I think, just one cluster of 4 cores or less, of course. And then within the core, what you have is you have this level 1 cache and you have a level 2 cache. And the level 2 cache is shared amongst all the cores in a cluster. And the important thing to understand about caches is that the like closer it is, the faster it is to access. So when a CPU is doing its job, it's getting instructions from memory and it's getting data from memory. And if that data is or instruction is in main memory, it can take actually a long time to even just load it, which means that like your execution speed is going to be really slow, because even though your CPU is really fast, it doesn't have the instruction to actually run. Cache talk once with cashews. Yeah, I go for some cashews. So the only way that you can get really high speeds on a CPU is if your instructions and your data are really close. So that's why these like level 1 caches. Hi, Alvaro. Level 1 caches are really important. And then the level 2 cache is the way that you can share between cores. And then the further away you go, the slower it is. So right now I'm running and I don't have caches enabled. So I think for every access and thing, I'm actually having to go to main memory. Now the CPU will be a little bit smarter. It will kind of like try to look ahead and speculatively fetch stuff still, I think. But it's still going to be really slow. So I think basically, and the reason to start with that is because there are other things. So remember that there are other things that we're sharing memory with. So in our case, the frame buffer is shared. So the frame buffer, we write to it and it's in RAM, but the GPU is also reading it to output. So we have to worry about that. USB does a similar thing. So like you'll say like, hey, USB, put stuff here, and then they'll fill it in and you have to make sure that it's correct. So if you don't do that correctly, what could happen is that like somebody else is writing main memory and then you're loading it, but you're getting a cached version. So it's actually old and stale and basically incorrect. So there's a lot of complexity around kind of keeping all the cores' view of the world consistent, which is why when you're bringing something up, you should not worry about it. Definitely don't worry about it in that case. So I think, I think kind of what I expect us to try and do is like we can probably get things faster to some degree today, and then like with more work you can get it faster and faster basically. So this is kind of cache basics, and right now they're just off. So they should be going to main memory for everything that it needs to do, which is going to be very slow. Sets and ways and blah blah blah. Yeah, if you want to see more details about this is a really good resource. I read it last night. This is talking about write buffers, write back versus write through. Not exactly sure what we want. So there's other like cache maintenance things you can do. So if you write a bunch of data and then want to make sure that main memory has it, what you do is you say you clean it, and that basically pushes that data all the way back to main memory. So like we could do all the frame buffer stuff and then clean it, and hopefully the GPU would see it. And then invalidate is the opposite. So if you're going to be reading something that somebody else had changed, you want to invalidate it and get it out of your caches so that you have to read it from memory again. Here's another, this is a different terminology thing. So inner versus outer. And I think in our case, it's probably both inner, but there's actually ways of discovering this stuff. So I thought we'd start playing around with this. One thing I think that I want to start with is, yeah, so I guess we should just get into it. First, I want to do a performance test. I want to be able to measure it kind of loosely. So I think I was thinking about this, and import time, and then we can do time.monotonic, and let's just do the nanosecond version. Oh, oops. Well, that's the first thing we could do, is we could turn on long integer support. Good night, Dave. Or we could just do time.monotonic. And the reason it's slow is because the display is still running. So if I go back to this, we should be able to see what I'm doing here on the display as well. So I wanted to do while, I guess, how do we do that fast? So what I was going to do is just, I guess I could put it in a function. So let's do that, t. So I'm going to do I equals 0, start equals time.monotonic, while time.monotonic minus start is less than 0.1, I plus equals 1, and then print I. That's right. Oh, it's so slow. So if we do t, so 57. Let me run it again. Oh, interesting. That's very variable. But hopefully the improvements we make are greater than that. Hi, Hams Labs. So we got HDMI and USB working on the Raspberry Pi on CircuitPython bare metal. All right, so we're seeing a little bit of fluctuation here, but I'm hoping we can get like orders of magnitude better, like in the thousands or tens of thousands. And maybe I should copy that. Let me just copy this so I can. It's because I don't have storage working yet, I'm gonna have to type it in every time we want to test. Although I guess I could do paste mode, but I don't actually know how to do that. Okay, so that's our first step, and the one thing I thought we could start with is, so the tricky bit is for the data that you're gonna share between yourself and a peripheral. That's really hard to get right. One thing that we can do, though, is that there's two different types of caches. There's instruction caching and data caching. And let's just take a look. Right now, we are... Where's our linker script? So when we lay out memory, we're putting, like, so in microcontrollers, we usually have flash and we have RAM, right? And the flash is where all of the stuff that doesn't change lives, and then RAM is where the stuff that does change live. But the way the Raspberry Pi works is that the bootloader reads our file and puts it all in RAM. And so right now we're treating all of RAM kind of as a read-write thing. But I think what I want to start by doing is just splitting our RAM back up so that we can have a section that's like cacheable, never going to change, like cache it as much as you absolutely want to, and then another region that we're going to leave as is because that's going to mutate and we don't necessarily want to maintain everything. So I think the very first step I want to do is I just want to set aside a flash version, a flash area of RAM, and then a RAM area of RAM, if you will. And luckily we have a ton of RAM, so we can basically do whatever we want, which is great. I think it does mean that it may start up a little slower if it has to like load the file, like a bunch of empty stuff between them. So we may not want to have too much of a gap just because it'll start up a little slower. But I figured that's where we could start. So here's what we've got. We've got this kernel load address. So this is where we start. And then text and read-only data are the things that don't change. And then data and BSS are the things that do change. So I think what I want to do is, I wonder if I can add different sections. I think I can. Where's where would have it? Too many things open. But that makes sense, right? Anybody have questions about that approach? Common template memory. So that's this, I think. So let's say that, should we call it, let's just call it read-only. Read-only is here. We can mark it whether we can execute or not too, but I don't think that matters. Our origin's gonna be 8, 4. And I think for length, what we want to do is we want to match it with, so we're gonna have to change our MMU settings. Normal. And let's just do read write. And that's gonna be origin equals 0x8000 plus 1m. I think it's 1. We'll see in just a sec. Basically, I want to make it with an easy page table size. So then what we do is this goes into read-only. This goes into read-only. This goes into normal. And so does this. And I think these might want to be in here. I don't know what this BSS size is, but I'm going to leave it in there. Oh, good, you can see what I'm doing. So the next thing I wanted to check was the MMU fact, I think I might have it noted. I mean, I could just do it. I have a 2 gig module. I shouldn't do that. I think I really do want it down to, what's this say? Each entry is a gig. And then, what is the second table's size? ARM MMU page table tool. This is the person that had the good article about it. Like the finest unit is 4K. And then what is the next smallest unit? Each table is 64K. I think it's actually in this video. It's a like really good diagram of it. Two megabytes. Yeah. Go away. Yeah, so there's the 1 gig and then there's the 2 megabytes. So we would need instead of this 1 gig table, we're going to need another table of 2 megs. So we're going to need this level 1 table still, but we're also going to need a level 2, which goes to 40, I think. That's what a gig is, right? A gig is this. So this will be there. I don't know my hex digits that high up. That's my problem. So our first entry is not going to be that anymore. Our first entry is going to be this other level 2 table that is 0, 0 to 4. So I think what we'll do is we'll just do, well, how much is 2 megabytes? I don't even know. Like in hex, what is 2 megabytes? It is 2 times 1024 times 1024. Right? Kilobytes, megabytes. So it's 200,000 if you read it that way. So what is 80,000? That's where we start. 80,000 is 512K. Right. Okay, so what we can do is we can do the first. We'll do the first as the first 2 megabytes range. That'll be the stack, and oh, it'll be the stack. That's probably okay. That's probably okay. Except for the mailbox stuff is all done on the stack. which maybe we could just figure out how to fix. Yeah, let's do that. Let's get that working. Base hex because of Traveler role-playing game. Okay, so we're now setting up this first gig. Oh, you know what? And we also have 16 megabytes at the end of as frame buffer memory, which we don't need to read. Or like it's not going to change on us, so we could cache that. We can, yes, I think we can figure this out. Stack code ROData and then data BSS and and then GPU. So what we're gonna do is the first entry of this is the first 2 megs. And this is where, if I mark these tables as const, that's where these tables will live and make them cacheable as well, which will be good. And in fact, I don't know why this is marked volatile. This should really be const. I'm gonna break stuff. That's why I was like, let's commit this before I start breaking stuff. So we're pre-computing this all. No, we're not. We're filling it out here. Bummer. Reflecting me, very interesting. Looking forward to seeing this on the Pi 4. Thank you. It should be cool. Okay, it doesn't need to be const. It just shouldn't need to be volatile either. It should just be able to live in normal memory, and maybe we can figure out how to make normal memory cacheable. Break stuff, smash it. I'm trying to make it faster. Okay, so level 2 entry 0 is going to be equal to basically this. Maybe I'll set it all up as the same and just make sure that it's correct. We're still running. So first 2 megabytes is gonna be that. And actually the remainder it will as well. Base 0. Actually, we could just we can add this execute never flag, right? We have a good way of catching the exceptions now. This is gonna be this level 2. And everything after that is gonna be execute never, but normal caching otherwise. And we figured out that we have to have the access flag set. This we don't need anymore. And let's do it. Let's do this down below too. Okay. All right, so the only change that we should see is now we're doing one more level, one more page table level. So now we can do 2 megabyte chunks in the first bit. And everything's set up the same. Did I copy this twice? Looks like I did. Like we don't need the second copy. Okay, so this is, I think I wanted to read like first to the end. So this is the first 2 megabytes. This is the rest of the megabytes in the gig. And then we set the top level. And then we do the next, we do the third gig. We ignore the first bits and then, yeah, so I think that's right. So I think that's correct. I didn't finish the linker changes. So let's just do 2 megabytes there and 2 megabytes there and actually this is going to be 1.5. And then this is just going to start at 2 megabytes. And the length of this is actually 1022. Right, so that's the first gig. Maybe. Should we see if it works? See if it compiles. Let's clean. Syntax error on line 6. Why is that? Origin length. Do they need to be comma separated? No. Can the origin not be a size? That's possible. What did we decide? 200,000? 2. Yeah, I get sashes I lose track of. Still syntax error. Do you think this normal is a keyword? RAM. I don't see a reason. I mean, maybe the line number's off? Is this length wrong? There's me trying to get the LED on GPIO 14 to flash. It's taken weeks and weeks to get here. I mean, maybe it's that. Let's just say it's 1. Yeah, it was that. 1024 plus 512. What is it? Is it 1536? 15 something like that? Times 1024. Oh, I was right. Okay. Can't do points. All right, it worked. All right, so let's turn this off. I was not expecting that HDMI converter box to work, so I'm pretty excited that it is. Did I ever clean? I didn't. Oh, maybe I did. Yeah, I did. Okay, copy it over. Yeah, so it's a lot bigger now. It's 1.5 megabytes. I do math on Friday. Yeah. I try. It should be more than 1.5 actually, but let's just see if it boots up. Hopefully it will. Otherwise we can GDB it. So the bootloader. Hey! It still works. Awesome. That's good news. Okay, so the next thing we want to do is change the MAIR. MAIR controls some of the cacheability properties of the memory. 1.5 megabytes, what is this, on Electron app? I don't know. I think it's, I mean, most of that's zeros too, I guarantee it. Because we just moved all of our data out. It only added like a megabyte of empty space. It's fine. This is a whole new world. It's a whole new world of having like gigs of everything, which is pretty wild. Oh, and it worked even though we set execute never. So let's pull up our architecture. I think I have it open here. Architecture reference. Am I on it? Holy moly. This, oh, look at that. It's the last thing I looked at. Okay, so this is, so the way that the memory attributes are stored is that the page table, which is the thing we were just editing, has an index into values in this register, the MAIR register. So when we're setting like this MT normal NC, so that's normal memory not cacheable. And then we have this device not NG NRE NE, which G is gather, E is early write. Anyway, it just makes like, it's right. That's the right thing. And if we look at, so I cribbed this setup stuff from one of the examples. If we look here, we can see that like index 0 is this and index 1 is this non-cacheable. And the flags for each of those are zeros and 4. So I'm going to actually want to add another here, just define mt read only. And we'll set that as 2. And so this is like stuff in RAM that's not going to change, that we can share with whomever we want to share it with. 0x00. Actually, we can do it as 4 just to be safe. And then here we want to do yeah, the RPy bare metal OS is one of the resources I've been looking at. You can find it on GitHub, and I've been just looking at the GitHub version. But nt read only flags, and we're gonna scooch that over 8 times mt read only. And we're gonna want to put flags here. It's raining. And so let's dissect this. So each MAR is 4 bits. So if we see attributes here, device memory is if the top bits are all 4, and then D tells you something about it. But we want normal memory. So normal memory is if the O's are not 0 and the I's are not 0. And I think the O's and the I's here are is outer and inner. So if we think back to the diagram I showed earlier where like L1 and L2 were inner and then outer was L3, it's a way to like have different policies for different parts of it. I think that's what it is. Here you can see, here's the device stuff. And it's, yeah, it doesn't tell you, like N, it's 3 bits and the N tells you whether it's not set or not. I think it's like gather, early, write, and I forget what the R is. It's in that, the thing I read last night that we linked to. Okay, so here is how O is. We want, we don't even care about writing because we're not going to write it at all. So we can just do it as, I don't know what transient is. Oh, RW might be read write. Does that make sense? Normal memory. Non-transient. What the heck does that mean? I mean, the R and W bits have the following meaning. Allocate, not allocate. But we do want to allocate it. So we're set up as 4, which is this right now. So we're not allocating it to the cache. But for, I think we just want 3 outer right back. I think we could just set them all high to F and we would be set. I think I saw that somewhere else. So let's do it. So this is like aggressively cacheable. So if we go back here, and for this first 2 megabytes, we're going to call it NT read only. And where did we find out? Always wondered what the not garbled alphabet soup was. NGNRE NRNE. Did you look it up or do you want me to look it up? Because it's in this Cortex-A series thing. There's a whole section on cache coherency that talks about it. I just don't remember what it is. Okay, so this is changing it to read only. And let's just see if we can't find the access flags thing. Let's see if there's any other settings that we need to set, because I think there are. Access flag. Where is that? It's the long form description of the memory. Oh, this is not going to work. Oh, more than 1,000 matches. That is the wrong thing to search for to find this. You know, it's probably if I just look for the mirror references, I'll find it. Oh, there's still 600. Oh, but it might just. Implementation defined attributes. Long descriptor format translation tables. That's what I'm looking for, but you haven't linked me to it. That's a lot of tabs for a Raspberry Pi 4. Accessing it. Long descriptor. That's what we want. Long descriptor format. I think it's this. Ooh, that looks nice. There's the 2 megabyte region. Ah, here we go. This is what we want. Upper block attributes, lower block attributes. Block table. Level 3. We're not in level 3. Stage 1. Security bit. AP table. AV832 long descriptor. Page-based hardware attributes. Non-secure EL2. Execute never. Privileged execute never. Indicates that 16 adjacent translation table entries point to contiguous memory. I wasn't doing that because I didn't want to. Not global bit. Access flag. This is global, so I don't think we want to set it. Shareability. That's the thing that I'm thinking of. Access permissions, not secure. And then the attribute index. But we're in stage 1. EL2, non-secure, EL stage 1, memory attributes for the shareability field. This is what I was thinking of. Memory region attributes. Aggressively cacheable. That's right. I'm going to aggressively cache it. Overview. Shareability. Outer shareable. S-bit. I don't know what this text thing is. Shareability. It probably doesn't matter. Long descriptor format region attributes. Indicates the mirror register to be used. Shareability long. Okay, so here. Both inner non-cacheable and outer non-cacheable. Shows the encoding of this field. So right now it's marked non-shareable. But we want it to be. So we want it to be inner shareable. Yield to control of non-secure memory region attributes. Mem attribute 3 and 2. Is that separate? Oh, this is stage 2. These things are so complicated. Combining the cacheability attribute. Shareability attribute. TLBs. Okay, great. Ideally, we want to cache that too. We just want to cache it all. We want to be aggressively cacheable. We're about to run out of time, though. I'm not sure I'm going to be able to get this actually done. Do we remember what bits are shareable? Because we can set it as inner shareable. We know that. Shareability long descriptor format. It's linking to itself. Links to itself. Inner shareable. Okay, shareable looks like it's 8 bits in. So let's just do outer shareable, the TCR value. Is that better? I think that is better. I don't know. I don't think it really matters because we're running on a single core. So that's these flags, but we want define descriptor outer shareable. Right? That's not the right thing. Yeah, it's bits 8 and 9. And it's just like, how do you document all this stuff? It's just so much. Normal memory long descriptor. Okay, so outer is 1, 0, inner is 1, 1. Let's just add them all. 1, 0. So I don't have to think about this again. Is 1, 1. And the last one is, I think there's one more. Oh, non-shareable. Okay. Let me shift no bits. Non-shareable. Okay. I think we want to be, I don't know. Inner shareable versus outer shareable. I thought you would say both. Anyway, let's try it. Let's say inner shareable. Then how do we turn the caches on? I think they're in this system control register. SC. System control. Look at all those bits. 64 of them to be precise. It may not be the system control register. I should probably look for a tutorial. Branch type. Branch predictor would be good if we're not doing that. Trap, cache maintenance. Endianness. So much complexity for like doing isolation and things. Instruction access cacheability control for accesses at EL2. When EL2 is enabled in the current security state, and E2H and PGE equals 1, 1. The I bit. All instruction accesses to normal memory from EL2 are non-cacheable for all levels. 1 has no effect on the cacheability of instruction accesses to normal memory from EL2. And right there, by there. This bit. So if it's set to 0, I think it's basically off. I think we do want to set bit 12 to I. So that's coming from this. Oh. We're ORing it. Bit 12, bit 12. Bit 12 is 1, 2, 3, 4, right? 4, 8, 12. Bit 12 is actually the 13th bit. Turn on the instruction cache. I think that's what it is. Mark Olson says, so what's the current status? What did you get to work so far? I see something rather cool in the bottom right hand of your screen. Yeah, so HDMI is working, and that's what in the bottom right hand side you're seeing the current HDMI output. And that's 640 by 480, and it's pretty slow. So what we're working on here is we're trying to get the cache going so that we can be faster, hopefully. So maybe I'll just try to see if we can turn on the instruction cache here and get things going a bit quicker. And USB is also working. Not mass storage because we don't have the storage working yet, but USB CDC is working. And so we're just trying to, I'm perusing all these bits in this register to figure out how I can turn on the caches so that it's not really, really slow. Alignment faults, which we're not having a problem with. The C bit. Oh, this is data accesses. These are just like overrides. And this is bit 2. Let's, oh no. How did I? Oh, I got to the end. So we're setting bit 1. It is major progress. Why am I? Oh, I'm too far away. So this is setting, turn on the instruction cache and turn on the data cache. Let's just go for broke, shall we? Data cache is bit 2. I guess I could do this all at once, but bit 2 is 4. Is the plan to have the Raspberry Pi show up as a mass storage device like other CircuitPython boards? Yes. Once the storage is working, then we'll have it do that too. A lot of the Raspberry Pis are not necessarily, the boards themselves are not designed for that to work though. So there will be caveats around some of the boards. All right, let's let's Hail Mary it. MP read-only flags. Did I name it wrong? MT. Where did it go? MMU 321.25. Here. I'm in the habit of doing MP. Immediate out of range at operand 3. Oh, that's right. This the immediate encoding is really interesting because it's like a certain number of bits and then you can shift them. So, which is why it's complaining about this one where like the bits that are set are too far apart. But we don't actually need that top one bit because we're setting it for the instruction cache. So what we're doing is we're reading the value, we're doing 3 things, and then we're setting the value, and then we are turning on an instruction boundary. This probably won't work. It may work, it may not work. We will see. But if it does work, hopefully it'll be quicker. Like, I generally don't like to prematurely optimize, but like that, it's pretty slow. It's pretty slow. Sync. As I understand it, that's the reason for using the Pi 4 or Pi 0 is they support setting a USB port to a mode, USB-C port on the Pi and the second port on the 0. And the 3A, I think, they're A connectors, but they can do OTG, I think, as well. Interesting. I'm excited to see what CircuitPython can do on a Pi board. I was curious how well they would behave as mass storage since they're closer to being a full-fledged PC than other CPU devices. Oh, doesn't look like it worked. We're getting the rainbow test pattern. Let's just see what openocd says. We can connect to it, which is good. Oh. Allocation outside of EM. New exception. Value error. This could be a data thing. Let's just for now, you need a converter cable, yeah. Let's not do the data cache. Let's just do the instruction cache. Because clearly, like, this is a data problem, but we should get some speed from just doing the instruction cache. And that should be safer because that's like not data that we're sharing with things. So let's give that a shot. Which I think is what I should have done in the first place. Let's just do instruction cache first. Because we know that the code is not changing at all. We don't have to worry about managing it at all. We're not doing, like, if we had like the native emitter going, then it would matter. Because then we're actually going to execute from somewhere else. But that is not something I care about, especially right now. Cache maintenance is a pain. Bootloader. Heyo. Ooh. Is that quicker? Not really. Let's switch to it. All right, well, what was the test that we did? Let's see if we gained any sort of speed. you can't see my desktop anyway. Def t I equals 0. Oh no, I didn't import time monotonic, which I think is fine. Time.monotonic. And we don't have long its on. It feels, this is feeling a little bit more responsive, which is nice. Oh no, it went all the way. Now end it. Yeah, the scrolling are a little painful still. Zero. Just a little bit. Huh. Well, we're in the 600s still. Feels a little quicker, right? Can you paste in that program? I might have been able to. It was a... All right, well, obviously we have some more optimization to do. Getting all the caches going. Like there's a cache for the TLB as well, so doing all of the memory accesses stuff, and I don't know if that is on. That's another thing that we could turn on potentially. We've got a few more questions and then we'll wrap it up. How is the storage, etc. working now? Do you have an eMMC model and use the USB boot thing to copy it over, or I'm using an SD card. So the bootloader is loading from the SD card into RAM, and then I'm running. So I don't actually have the eMMC stuff working from CircuitPython yet. I think it is a smidge quicker. I could run these tests with the display off, and it would be a lot more reliable, probably. Next question from N. Lindholm is it still recommended for beginners to start with CircuitPython 6? I've been finding some of the sensor examples provided don't work with CircuitPython 7, as the calls, functions, etc. have changed. I recommend starting with 7. There's a lot of good stuff in 7, and it seems to be stable. If there's stuff that's not working, please make sure that we have issues filed for them, because we would want to fix them. We're already talking about doing a 7.1, so we're definitely past 6 at this point. And then Toddbot asks, big question, if I submit a PR that allows booty.py as code.py alternative in the pirate language mode, will it be accepted? I would accept it, but I would argue that booty.py is probably more an alternative for boot.py because they're very similar. But yeah, generally I'm open. Well, Timon says eMMC and SD card would behave the same, nothing to do there technically. Unfortunately, the Raspberry Pi does have 2 different ways of managing SD cards. It has an eMMC peripheral from some company, and then they also have a SD host peripheral that is from that is like custom. They're both supported by Linux, so you may not know which one's which. The eMMC one can do SDIO for like Wi-Fi stuff. So I was just looking at this, and like for the Raspberry Pi 3, the eMMC peripheral is used for the Wi-Fi, but the SD host one is used for the SD card. So things like that. Related question, is it possible for the community to offer pull requests to update those examples? Would that be best done on the particular sensors GitHub page, which then would filter to learn.adafruit.com? So yes, so there's kind of 2 places to look, and yeah, pull requests are definitely welcome. we have it so that if you see code from GitHub in Learn, updating the GitHub repo will automatically update the Learn guide. So there's two places to look. There's the driver specific example, and then there's also one massive repo for Learn guides. So there's two places to look for where the example code would be for a particular sensor. Yeah, feel free to bug me on Discord more if you need guidance and have thoughts on that. Okay, thanks Minnesota Mentat, and I'll switch to here. So running CircuitPython from a multi-gigabyte SD card will just work on the Raspberry Pi. Hopefully, yeah. When we're done, we'll both have multi-gig flash, and multi-gig RAM, which will be like, right now it's just 32 megabytes, and like, I don't know what to do with that many megabytes, given that like maybe we have like a microcontroller board with a single megabyte. There's just a little bit of math we have to do to figure out like how much room we have between CircuitPython and the GPU, and then we could use all that for the heap too. But I'm not sure how well the GC and everything will perform when it's actually that huge. So hello, goodbye, I don't know. I'm Scott. This has been a deep dive. They happen every Friday at 2 p.m. Pacific. That's 2 p.m. Pacific regardless of time zone. So if you're in Europe in a few weeks, or if you're outside the US in a few weeks, the US will change and shift things for you. You can join the Discord server by going to adafru.it/discord. We chat in there all the time. And if you want to follow CircuitPython development, there's a CircuitPython-dev channel. There's also this live broadcast channel that you see next to me. You can chat with me there. There's also a deep divers role, so ping me and let me know you want to be in the deep divers role. If anything wants to, if I ever switch things after I've like kind of announced them, like next week is on Friday, which next week it is, I'm planning on doing it on Friday, but if I change my mind, I'll ping the deep divers role. So make sure you get that. Thanks again to TAC for helping with the USB stuff and making tons of progress there. Thank you to everybody who's done bare metal Raspberry Pi resources. It's been super helpful, and hopefully this is just another one of those things. If you want to support me, you can support me indirectly through Adafruit by going to adafruit.com and purchasing hardware there. All sorts of cool stuff that runs CircuitPython, and we're just going to have like a larger and larger collection of different boards that have different strengths that can do CircuitPython. So that's great too. Next week's on Friday, and I will adjust cat cam because I pet the cat on the way out. But also thank you to Patrick and David for taking notes, and Patrick for organizing those notes into the deep dive notes repo under the Adafruit org as well. So thanks again, and I'll see you next week, and maybe SD card will work and we'll have the drive showing up and it won't be super slow. Fingers crossed. If you want to follow along, I do push all my work to GitHub pretty much every day. So if you want to try this out, you can go to github.com/tannewt/CircuitPython, and then there's an RPi branch that has all the latest Raspberry Pi code in it. And with that, I'll pet the cat and we'll get out of here, and have a great weekend, everybody. Go get your hair cut if you need one.